Good morning. In the last class, we have talked about the frequency response of sinusoidal inputs. We have seen that any system can be seen in the form of frequency transfer function and analogously written as in the transfer in the S domain as well, and analogously it can also be seen in the frequency transfer function, through which we have seen several systems such as first order systems and second order systems, and we have analyzed that what is the gain of output with respect to input, and what is the lead or lag between the phases of those outputs as with respect to the inputs for first order systems and second order systems as well. But in the last class we have not talked about what happens if the frequencies are varied for a range of values. And this we are going to do it through the help of this Bode plot. So what we are going to do, let's suppose we have any system g of s which is converted to g of j omega, and we are going to look at these magnitudes and the phi values, and we are going to seek what happens if we are going to vary the omega for a range of values. And why this is important? So this will help us to analyze the system's stability. But we are not going to talk about the stability phase or gain margins in this topic, in this particular course. And this demands this particular gain margin and phase margin concepts demands higher electrical courses such as control theory. So we are going to restrict it with this Bode plot only, and we are just going to seek how this frequency, if at all we are going to vary this frequency, how the magnitude and the phases are going to vary with this omega. So this is what the Bode plot is all about. So let's first see, for a simple GS, let's suppose I have a GS in the form of some constant K. And let's convert it into the frequency transfer function. Vj omega is again K, since there is no S term here. The Bode plot is nothing but it is the plot of the magnitude with respect to the frequency for a range of frequencies, and these two plots are taken in log scales. So essentially this magnitude is it is in dB, and we are going to convert this magnitude in dB. And while to convert it, there is a convention that we are going to, whenever I want to write the magnitude in dB, write the magnitude in decibels, we are going to multiply it with 20 into log of mod g j omega. This is what our convention would be in the y-axis, and omega will be taking. So this is the plot of magnitude versus omega plot, and similarly we are also going to plot the phases phi with respect to omega in log scale. But this phi y-axis will not be in y scale, it will just 0, 90, minus 90. Okay, we are going to plot in this way. So let's first talk about this transfer function, how this transfer function behaves with changing frequencies, band of frequencies. So this, since this is a log scale, there is no 0 here. The 0.1 will be here, 1, 10, 100, 1000, and so on here also. So since we are going to take this function, particular function, so we are going to convert this into dB. So in dB I can write, and we are going to write 20 times log of mod g j omega, which is nothing but 20 times log of k, mod k. Okay, so since k is independent of omega, no omega here, so it will be a straight line. It will be a straight line like this. This function is 20 log of mod of k. K will be some constant, like let's suppose k is 10 for the time being. So my magnitude in dB will be 20 log 10, and this 10 log 10 base is always in 10. So I am going to write 10 base 10, 1, so 20. This magnitude is 20 dB. So this line is 20 dB line. Similarly, the phi I am going to calculate tan inverse imaginary part divided by real part, right? So imaginary part here is, since this is a purely real thing, plus imaginary part is 0, tan inverse 0 is equal to 0 degree. So your phase is going to look like on this line. Now let's talk about another case where my GS is 1 upon S. Now let's convert it into the, we want to seek the frequency response, so we want everything to be converted in GJ omega domain. It is nothing but 1 upon J omega, and let's write it in this form. Let's multiply it with J both sides, so we are going to get minus 1 upon omega times J. Okay, this is what your transfer function, frequency transfer function is to look like. Now let's calculate what should be the magnitude in dB. In dB, magnitude will be 20 times log 10 GJ omega is equal to 20 times, so 20 log is a convention. So it comes from the electrical engineering background, convention, and so we will follow that in this whole context. So log of, so what is this? Under root. So what is my gj omega mod will be under root 1 upon omega square is equal to 1 upon omega, right? So this is, so this is 1 upon omega. Okay, I can also write 20 times log of omega to the power minus 1, and we can now write minus 20 log of omega. So this is how your function is going to look like. Okay, so now let's talk about in this the same scale how this function will look like, minus 20 log omega. So now I'm going to plot minus 20 log of omega. So let my omega is equal to 10. So your magnitude will come out to be minus 20. So at omega is equal to 10, the things this is minus 20. Wait, yes, so let's start from so let's take omega at omega is equal to 0.1. So 0.1 we will be getting magnitude of 20 dB. So 0.1 you will get 20 dB. At omega is equal to, let's suppose 1 log 1 will be 0. So your magnitude will be 0. So 0 will be somewhere, let's suppose this is my 0 line. So this line is here, and this line is this frequency is 10. So 10 we have minus 20 will be somewhere here. So we'll see there will be a negative slope like this linearly, right? We'll get this line. So this line essentially will be minus 20 log of omega. This is how your frequency transfer will vary as you tweak your omega. This is how it will change. So now let's talk about how your phi will change. So phi is nothing but tan inverse this will be not the mod here. So tan inverse imaginary part is here is minus 1 upon omega divided by 0. So tan inverse minus infinity is equal to minus 90 degree. So this functions phi minus 20 log omega. So sorry, minus this functions phi will look like this. So this is your phi 1 for first case, this is your phi 2 for second case. Okay, now let's talk about the third system. Now let's see, your GS is 1 upon tau s plus 1. So this is a typical first order system. Now let's convert into GJ omega form. So 1 upon j omega tau plus 1 is 0 function. Now in magnitude in dB, in decibel, you will write it 20 log 10 base So you will get something like this, 1 upon under root 1 plus omega square and tau square. So this is what your magnitude, how the output to input, the gain will vary. This is the ratio of output to the input. Okay, so if we talk about it here, again here itself, so here there are two things. So let's take it a little bit in the next page. So we have magnitude 20 log base 10 1 upon under root 1 plus omega square tau square. So let's suppose when my omega is much less than 1 upon tau. Let's suppose this is the case we have. So when omega is much less than 1 upon tau, so this dB thing, this whole thing goes to 0. Right. So you substitute here, omega times tau is much less than 1. So this is the one factor here which is less than 1. So this whole thing boils down to omega log 1, which is nothing but 0. So for low frequency or lower than 1 upon tau, your magnitude tends to go to 0. Now when omega is greater than 1 upon tau, what happens? This is much greater than 1. So this one term we can ignore now. Now we can write this thing goes to 20 log 1 upon omega tau or minus 20 log omega tau. This is how will behave if your omega are greater than 1 upon tau. So this 1 upon tau is a critical frequency. This frequency at omega is equal to 1 upon tau, this frequency is called corner frequency. Or breakpoint. Since if you talk in terms of, so let's put it in here. So till omega is equal to 1 upon tau, let's suppose my tau is equal to some number, let's suppose some number, we can take some number, let's suppose 1 upon 5. So tau is 5, let's suppose. So my omega is equal to 1 upon 5.2. So till 0.2 radians, till 0.2, from 0.1 to 0.2, let's suppose 0.12 is here, 2 is here. So till 0.2 what will happen? Everything goes to 0. So your function will look something like this till here, and after that what will happen? Whenever it crosses this corner frequency, it follows this function minus 20 log omega times t. So it will go something like this. So till now it will go like this, and then after that it will go like this. Right. So this is what it signifies, minus 20 log omega tau. right? Now let's talk about the phases. How does the phase behaves? So phi is equal to tan inverse minus omega tau, if we talk in terms of phases. This is how it will look like. But let's do the analysis. Whenever omega is much less than 0.1, by tau. So essentially omega tau is much less than 0.1. So we'll put it here. So we'll get phi is equal to tan inverse minus 0.1, right? So at these values, so where things are going to switch. So basically at omega is equal to 1 upon tau, things are going to switch for these things. But here what will happen, and let's suppose omega tau is equal to 10. What will happen? Tan inverse phi is equal to tan inverse 10. So it goes to, so how your tan function look like? Pi by 4, pi by 2. So this is your 0, this is your 1, this is your infinity. It goes like this, right? So you will get a higher number, 10 or so. So this is, let's suppose this is your 1, this is your 10. So you are going close to, so higher the number, you are going close to pi by 2, 90 degree, right? This is 90 degree, and this is since minus is there, so this is minus 90. So phi is 90 degree at higher numbers, right? So at higher frequency, things are going close to minus 90, and if it is lower than some certain limit, it keeps on, it goes to 0. It is close to 0. So how this thing will be represented here? So this thing will be represented like you will have till some part you will be having 0, and after that you will achieve minus 90, right? So you will go something like this and you will achieve this. See, you can see the differences. This is your constant function, this is your 1 upon s thing, this is your first order system. And similarly in let's suppose this is my phi 3. Similarly in gains also, phases also. This is how the change of frequency, it will parameter will be changed. Now let's talk about what will happen if we have second order system. Let's suppose Gs is equal to omega n square. This is your natural frequency, not this omega. S square plus 2 zeta omega n plus omega n square. These are omega n's are natural frequencies. S will be replaced by j omega now in order to find the frequency response. Omega n square minus omega square plus 2j zeta omega n omega. Now this omega comes into picture. This is what we are going to vary. Omega n will be fixed when the system is fixed. Omega n square. Now in dB, your magnitude will look like 20 times log of, I will do in one shot. So if you do the calculations, you will get log of under root 1 minus omega by omega n whole square, and this one again whole square plus 2 zeta omega by omega n whole square. This is how you get the magnitude. So again, let's do the analysis for smaller frequencies. Let's suppose for omega by omega n is equal to or less than, very less than 1. This is very less than 1, so this goes away, right? And everything boils down to 20 log 1, so 0 dB. So at till omega is equal to omega n, everything till omega n, so if at all omega is less than omega n, for all those frequencies, for lower frequencies, lower frequencies, things are 0, right? Now for omega by omega n, if it is greater than 1, so this thing tends to this value. If you do the calculations properly, you will get this value, log of omega by omega n whole square. So what we see, whenever this omega increases by 10 factor, so 10 factor, so this log of 10 is 100, log 100 is 2, so it is multiplied by 2, so your dB will be minus 40 dB, right? If you talk in terms of dB. Okay, and this will follow this function. Okay, and this function is a again slanted function. So for this, corner frequency is at omega is equal to omega n, corner frequency, where your gains switches. Okay, now let's talk about how does it look like in this log scales. Till omega is equal to omega n, let's suppose this is my omega n, let's suppose some number, let's suppose this is my, okay, let's suppose here, so this is my omega n for the system. Till this number, things will be 0. Okay, I'm sorry, 0 is here, sorry, so this is 0, till here it will be 0. Not here, close to here, so lower frequencies will be here somewhere, and this function is the slant function, and this would look like something like, this would look something like this again. So this function is nothing but minus 20 log omega by omega n whole square, and these two matches at omega n, right, asymptotically. So for the damped systems, for second order damped system, it should look something like this. Higher the zeta value, it will go something like this. So this is lower zeta values, so zeta is equal to 0.1, zeta is equal to 0.2, and the overdamped cases zeta is equal to 1 is this case. This is how a typical second order system would look like. And this at omega is equal to omega, and you will have resonance, you will have a higher peak. And we in reality also we incorporate this such kinds of pictures. Similarly, if you do the analysis for tan, the phi values, phi is equal to tan inverse minus 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So if you see that, if you do the analysis properly, so what you will get is something like this. We'll have minus 180 here, this 180, and this will be your omega n frequency. So at this omega n, things goes like this. Okay, so higher the value, higher the zeta value, higher will be the abrupt change in the shift of angles. This is lower zeta, zeta is equal to 0.1, this is zeta is equal to 1. This is how your Bode plot looks like on all the for all the transfer function in single plot. But in general, we do not encounter the single transfer functions all the time, right? What we can we usually get is the general GS might be in the form of G1s times G2s times G3s dot dot, and we want to plot. So you may have these transfer functions in series and so on. So in Gj omega you can write G1 j omega, G2 j omega, G3 j omega. Now in similar analysis, in complex analysis, what we have written x plus iy is equal to nothing but your mod of G1 j omega. Suppose I am talking about this first thing, times cos of phi 1 plus j sin phi 1, right? This is the magnitude, this is the phase. This is how your we have already talked about in phasors. Similarly for suppose x1 y1, so for this one and this one also you will write, and you will write in clubbed form. We can write G j omega in the form of G1 j omega, G2 j omega magnitudes, G3 j omega times cos of phi 1 plus phi 2 plus phi 3 plus dot dot, all the angles will be added, j sin phi 1 plus phi 2 plus phi 3 dot dot, all the angles will be. So effectively the magnitude of the whole function will be this one, the multiplication of all the magnitudes, and the phi's are phi 1 plus phi 2 plus phi 3, right? So let's take an example, quick example. Let's suppose my GS is 2.5 divided by s upon s square plus 3s plus 25. So here we can see we can split things in this manner, that I have G1s is equal to 0.5, that is a constant, G2s is equal to 1 upon s, this term, and G3s is equal to 1 upon s square plus 3s plus 25. Now individually you can treat all these functions and you can plot it, or either you can do individually and you can plot it as a sum, or you can directly go by this. So you will take the magnitudes of, and you will get the overall magnitude minus 20 times log of this will be your dB thing, and all the phases collectively will tell you the final phase angle. So I've already talked that I'm not going to talk about the stability, gain and phase margins. Okay, so one point I want to make is, higher the gain and phase margins, higher your system will be stable. So with the help of Bode plot, you are actually going to get the phase margins and gauge margins, and with that you can design your any system to keep your gauge margins in the stable limit. Okay, that's it for today, and in the next class we are going to talk about the closed loop controls, in which we are going to talk about proportional, integral and derivative controls, PID controllers. And probably this will be the last chapter, and there will be few other chapters which I am going to send you through the PPT, and this will be the last video lecture which I am going to make on PID controllers, and rest of the topics I will put it in PPT. Okay, thank you.